Hi everybody, it's Jake from Ginkgo Bioworks. Today we're doing a tutorial for how to use our new model API for protein engineering. Amino acid 0 or AA-0 is a protein sequence model developed at Ginkgo and trained using our in-house sequence library. I want to run this basically like a live demo where we code something in real time. We're going to be working in Python, but I'll keep it super simple. So if you have any experience in Python or another language, you should be able to follow pretty easily. We're going to write up a Python notebook where we import a protein sequence, mask a couple of the amino acids, and then use a mask fill transform to generate new amino acids for those positions. This is something you might want to do as a protein engineer. For example, if you wanted to modify or improve the function of a particular protein, and calling the mask fill transform of AA0 is going to be fundamentally similar to calling other functions through our model API and to calling other models that we have hosted on our platform. So once you can do this, you unlock all the API functionality that we offer at Ginkgo AI. To get started, you're going to want to head over to models.ginkgobioworks.ai and create an account. The account is free and it comes with plenty of free inference tokens to run this tutorial with more to play around with. Once you're logged in, you can see the models we've currently got available. As of this recording, we've got three. We've got the AA0 model developed at Ginkgo, and we've got two versions of the ESM2 model from Meta Research. One with 650 million parameters and one with 3 billion parameters. ESM2 is basically the gold standard protein sequence model out there, at least when I'm recording this in November of 2024. AA0 has a very similar architecture, with the main difference being that AA0 got to see a lot more training data, about 2 billion sequences from the Ginkgo metagenomic database. But we're not here to gatekeep your model choices. We want this API to be super convenient and easy to use. We're happy to host our model, public models, whatever, so that you can shop around and decide what is best for your application. To illustrate the comparison, I set this up as a tutorial for a little protein engineering challenge. We're going to try out AA0 and ESM2 side by side to see if they can predict amino acid changes to a particular protein that have already been shown to improve the function. It's just like a friendly competition, not a big deal, not meant to be a rigorous comparison of the two models because we're literally just modifying two amino acids on one protein. But it's fun. It's a fun way to see how the API works, and it gives us some stakes. Gives us a little skin in the game, which model wins. You have to watch to the end to find out. The protein we're engineering today is called PETase. This is one of my favorite enzymes. It's an enzyme that degrades plastic. Was discovered in 2016 near a plastic bottle recycling site in Japan, and it's interesting for applications in bioremediation. If you want to recycle plastic, if you want to get plastic out of the environment, basically having a really active PETase enzyme might help you do that. And then in 2017, a research group generated some very high quality protein structures of the PETase. They took a careful look at the active site and they were able to identify two amino acid changes that did improve the ability of the enzyme to degrade plastic. W159H and S238F. In other words, at position 159, they replaced tryptophan with histidine. In position 238, they replaced serine with phenylalanine. And it worked. They got a more active enzyme. Back in 2017, they had to do this manually without the benefit of AI. But I think it's a perfect little test case for the mask fill capability of AA0 and ESM2. If we go in and mask out positions 159 and 238, will the models suggest the improved amino acids, or will they revert to the original amino acids? Or will they do something crazy that nobody expected? Will they make the same predictions? We don't know. That's the test. That's the PETase challenge. So let's get to it. I'm going to code this up in Google Colab just because it's a super easy and user-friendly way to jump on a notebook and start writing, but you can feel free to follow along wherever you like to write your Python. Let's go ahead and start with some installation and imports. We're going to be using the requests package. This is a very popular package used for making API calls. And we're going to be using JSON for reading the outputs of our API calls. We're going to use the user data package from Google Colab. This is what is going to allow us to get access to our secret API key, the thing that you get from logging into the Ginkgo API portal that is going to allow you to make API calls. And we're going to import some packages from BioPython. These are going to allow us to handle biological sequence records in a natively biological format, which in this case is going to be the FASTA format. FASTA is it's just a popular file format for recording DNA sequences, protein sequences, and lists of sequences. One more little thing, we're going to import the time package. This we just use to pause briefly, which will allow our API call to complete so that the code can continue running and collect the data that we generate. All right, let's go ahead and run that. And what went wrong here? Okay, it looks like it wants me to install the BioPython package so that it's available in our environment. Let's go ahead and add that. Okay, looks good. Next, we'll want to collect the wild type and the engineered sequences of the PETase enzyme. So these are going to be the baseline sequences that we use to make comparisons among our models. We're going to get those sequences from the PDB, from the protein data bank. So if we take a look at this paper where they did the engineering work, I can scroll down and I can find the PDB record where they recorded the sequence and the structure. And in particular, what we want is this one, this 6EQE. Head on over to the PDB and type that in. And I get the record that we want, the crystal structure. And the sequence that we want, I think it's in here, this display files. Yeah, there it is, the FASTA sequence. So that takes us to the record in FASTA format, just some very plain text record of the protein sequence that we want. And if I go to the URL here, I can use this to download the sequence programmatically. So I'll go ahead and copy that. Come back into Colab and we'll make a wget call to download that sequence from the PDB. Let's run that. Now, if I open up the Files tab in my environment, I see this RCSB PDB 6EQE.FASTA. And if I click into that, now I've got the FASTA formatted, very plain text version of this sequence into the environment so I can start working with it. Next, what I want to do is I want to make some modifications to that FASTA formatted file just to clean up the formatting a little bit, make it a little bit more human readable, easier to interpret. I don't like this RCSB, PDB, 6EQE stuff. I just want to simplify it. So we're going to go into this this FASTA formatted spot file. We're going to read it with the seek.io package of BioPython, and we're just going to simplify it. So I'm going to change the ID field to wild type, indicating that this is the wild type PETase sequence. And I'm going to modify the description field, and I'm just going to give it something easy to read like PETase. Let's go ahead and check that sequence by printing it. All right, that looks good. Now what I want to do is just store this modified FASTA sequence as a new file. Man, these autocompletes are getting spooky good. But I don't want to call this PETase wild type. I just want to call it PETases because we're going to be using this same file to store all of the modified sequences that we create for this project. Go ahead and run that. Take a look at our files, and now we have this new file called PETases.fasta with wild type PETase and the sequence that we're interested in. All right, very cool. So we started from the primary literature. We found someone who had modified an enzyme that we were interested in. We looked through that paper. We found a PDB record associated with a crystal structure and with a sequence. Then we navigated over to the PDB. We found a URL associated with that sequence in FASTA format. And then we programmatically imported that sequence into our Colab notebook, converted it into a BioPython sequence so that we can work with it natively in Python. Nice job. Next, what I want to do is take a closer look at this sequence that we've downloaded. I want to look at the specific amino acids at the specific positions that we are interested in. This is going to act just like a sanity check. It's going to help us be sure that we are actually working with the protein that we are interested in. And it's going to get us ready to set up this mask transform because these are the amino acid positions that we are going to be masking and then using generative AI to regenerate. In this case, we're interested in 2 amino acids. At position 159, the authors mutated a W to an H. In other words, they replaced a tryptophan with a histidine. And then at position 238, they replaced an S with an F. That's a serine to a phenylalanine. All right, let's go ahead and check this. We're looking for a W at position 159 and an S at position 238. Okay, and that is completely wrong. What is going on here? Okay, so if you know Python, I think you probably already know the mistake that I made. I could feel some of you yelling at me through the monitor. The mistake here is that Python uses indexing from 0, whereas in biology, we index protein amino acids from 1. And so that M, that first amino acid of this protein, is actually index 0 as far as Python is concerned. And so that means that if we want the amino acid at position 159, we actually need to check index 158. And similarly, amino acid 238 is at index 237. Let's go ahead and check that. Okay, and that's what we wanted. We wanted a W at position 159 and an S at position 238. Now I want to create an engineered version of this sequence where we make these substitutions. We're going to put in an H at position 158 and an F at position 237. We're going to do that directly in the BioPython sequence. In order to do that, we first have to convert this into a mutable seq. That's something that we're allowed to make changes. And now we can make the changes that we want, swapping in an H at position 158 and an F at position 237. Now we need to create a new FASTA record for this engineered sequence. We're going to follow the same format as we did for the wild type sequence. In this case, I'm going to use for the ID field, I'm going to put in engineered to show that this is the engineered sequence, not the wild type. And for this description field, I'm just going to put in PETase, the same thing that we did for the other enzyme. Autocomplete's getting way ahead of me. Don't they know I'm trying to do this as a tutorial? I need to go step by step. I can't jump ahead. Just be patient, autocomplete. We're going to get there. Just hold on. Okay, that creates the FASTA record. Now, just to be extra cautious, let's go into the engineered record and make sure that we've actually made the mutations that we meant to make. Let's take a look at that. Beautiful. Okay, so this confirms we actually did make the mutations in the engineered sequence. Now let's go ahead and save that as a new record. We're going to add this engineered sequence to our FASTA file where we're collecting all of the sequences that we create. Go ahead and run that. Now if I open up my files, I go to the PETases.fasta, and sure enough, we've added the engineered sequence to our FASTA file. Okay, super cool. So we have modified some amino acid sequences directly in our Google Colab notebook. So the next trick is we need something to visualize these sequences. So I'm a biologist. I've been a biologist a long time. I love working with sequences. I do not read them directly from text files. I know, I'm not hardcore like that. I actually need something to help me visualize these sequences so that I can make any sense of them at all. And for that, we're going to be using a Python package called PyMSA-viz. MSA for multiple sequence alignments. This is a very handy little package for displaying sequences in a Python environment. So shout out to Moshi4 on GitHub for PyMSA-viz. Let's go back up to our imports block. We're going to install PyMSA-viz. And we're going to import a specific package called MSA-viz. Go ahead and run that. Okay, looks good. Now we're going to use that package to display the PETase sequences. We're going to give it our file name. Yeah, looks like autocomplete found it. We're going to give it some visualization parameters just to make it look pretty in our display, wrap length for how long the lines of the sequence are, and show count so that we number the sequence. And then we use this plot fig function to display it right here in our notebook. Go ahead and run that. And that looks pretty good. We get this nice looking multiple sequence alignment that is reading from our FASTA file. We've got the ID fields here, the wild type and the engineered sequences. And then we have the sequences color coded by amino acids so that we can easily see how all of the amino acids line up. But I think we've got one more little problem here in the way that we are doing our visualization, which is that this thing is just way too busy. There's too many colors, there's too much going on. I can barely even find the differences in these two sequences. I guess if I squint, I can see this W to H in position 159 and this S to F here at 238. But makes it very hard for me my poor eyes to pull out what is actually interesting. And so we're going to add one other visualization parameter here. We are going to highlight specifically the positions that we are interested in, positions 159 and positions 238. Let's try it like that. Very nice. All right, this is much cleaner. So now we have highlighted just the bases that we are going to be engineering for this project. Makes it super clear exactly what is happening to these amino acid sequences. All of the action is happening at positions 159 and position 238. Nicely done. We've got our sequences edited and visualized. Next step, we need to prepare this sequence for the actual mask fill transform. To do that, we're going to go in super low level. I am just going to manually create a string of the sequence file that we need, where we replace the characters that we want the Gen AI to transform, where we want to generate new amino acids, with a token that just says mask in string format. Looks like this. We take the wild type sequence from position 0 to 158. Then we add a mask token. This is how the AI model is going to know that's the position where I need to generate a new amino acid using the context of the entire rest of the protein. Then we go back to the wild type sequence from position 159 to 237. Then another mask token. Then back to the wild type for the rest of the protein. And let's go ahead and print that. And what did I do wrong? I got a name error. Yeah. Okay, that looks good. And so what we're seeing is a normal amino acid sequence, then a mask token, more amino acids, then another mask token, and then the rest of the protein. There's one more error that I've made in an earlier version of this tutorial that I had to cut, and I want to avoid making it this time. We want to make sure that PETase masked is actually formatted as a string because that is what the model API is going to want to read. So let's go ahead and check the type of this PETase masked. And we see that it's not actually a string. It's a BioPython formatted sequence. So if we try to pass that to the model API, it's not going to like it. So what I want to do is just recast this as an actual string. Now run that. Okay, and now we see we've got an actual string formatted sequence that we can pass to the model. And that means we're good to go. We're ready to use the mask fill transform. The next step is we've got to connect to the Ginkgo API so we can start making calls to the model. If you haven't done this yet, you're going to want to go to models.ginkgobioworks.ai and create an account. And then once you do that, you're going to get this very simple user interface where we've just got a block of code here that we're going to copy directly, showing how to make calls to the model for the mask fill transform. And then the other thing you're going to want to check out here is this API key, which is right here. I've got it blurred out so that none of you maniacs can hack my account, but you'll need to add this to your Colab notebook so that you can actually make calls. I'll show you how to do that. So you're going to want to copy this, go over to the secrets tab of your notebook. Let's create a new secret. We're going to call this Ginkgo API key. Paste the value right in there. Keep it a secret. And now we're good to go. We can access this as an environment variable to make our API calls. Go back to the home page, copy this code, back to the notebook, drop it right in there. This is going to let us connect to the Ginkgo API to perform the mask filling inference. And instead of just storing your API key in plain text like a maniac, we are going to go ahead and use userdata.get to get it as a secret environment variable. So what is all of this actually doing? We are just going to pass some JSON formatted data to the Ginkgo API through this URL, api.ginkgobioworks.whatever. We're going to pass it some headers to tell it what our API key is. We're going to tell it what model we want to use. In this case, we're using Ginkgo AA-0. So this is the AA-0 model. We are going to pass it some text. So this is the sequence that we actually want to transform. So we're not going to pass it this. We are going to pass it PETase masked. Then we tell it what transform we want to do. In this case, it's the fill mask transform. There's some code here at the bottom to collect the response of the API call. Oh, and we don't have to import requests because we already did that above. Let's go ahead and run that. Give it access to the key. And that is going to give us a new URL with a job ID that we can use to check the status of this job. So this is going to tell us when our job is complete. Let's take a look. And it looks good. It's complete. And we have got a new sequence. This is an AI generated sequence happening right before our eyes. Very cool. Now, I want to make a couple of changes here to this code that we copied directly from the website. I want to reuse this block of code to make calls for the other models so that we can collect all of the different sequences that we are going to compare. So I'm going to change some of the names here. Instead of just calling the response data, I'm going to call it API output AA0. And that's what we're going to print. And I'm going to add a note up here that this block of code is going to use the AA0 model. Go ahead and run that. And now all we need to do to run the other models on the same sequence is just copy this block of code and change the names. I'm going to change AA0 to ESM2 and collect the output as ESM2. Go ahead and run that. And then one more time for ESM2 3B. Go ahead and run that. What I do, okay, and that means I need to rerun this one because I stored the output in the wrong variable. If you want to know where I'm getting these model names to paste into the API calls, you can go to the Models tab of the Ginkgo AI homepage, and you've got AA0 650, ESM2 650, ESM2 3B. These are the model names that I'm pasting directly into the API calls. I'll go ahead and check the status of these jobs. That one looks complete. You can also check the status of your jobs on the usage tab here. It's got all the jobs that I've submitted recently and their status and their job ID and everything that I can find. Looks like everything's good to go. API calls complete. Was a very simple job, so it only took a few seconds to run. Next step is just to collect all of that data with another set of API calls. First thing we're going to do is just pause for a few seconds to make sure that the jobs have a chance to complete. We know that our jobs have already completed, but just in case somebody is coming in and they want to run this entire notebook from scratch, we want to make sure that the notebook makes enough time for the calls to actually complete so that the notebook doesn't crash. And now, yes, even the autocomplete knows what we want to do next. We want to get the results of the API calls. For this, we'll use requests.get. We need to add this headers structure so that we are allowed to access the results. And then if that works, we're going to collect the JSON formatted output. Let's go ahead and run that. Okay, that didn't crash. Now, let's print this output and see what we got. And I'm going to comment out this sleep thing so that we don't have to wait 5 seconds every time we want output. All right, here's what we've got. This very data rich but somewhat unwieldy JSON formatted output that includes things like our job ID, our error code, the job status, some information about the job, and also what we really want right now, which is the actual AI generated amino acid sequence. So the next thing that we've got to do is just crack open this JSON formatted data to pull out the sequence that we actually want. Looks like the part that we're interested in is with the result key. Take a look at that. And then it looks like we want the first entry on this list. So we'll take index 0, take a look at that. And then again, we want the result key. And then we want the sequence key. And now we've got, this is the actual sequence that we want. Full disclosure, I'm not really an expert in working with JSON formatted data. Maybe you are, maybe you know a better way to go into a data structure like this and pull out the string that you actually care about rather than kind of indexing it one at a time like I did. But, you know, got the job done. So we just want to store this variable as the actual AI generated sequence that we're interested in. And now we just repeat this for the other two models that we used. One call for ESM2. And one call for ESM2 3B. Swap out that variable. Make sure we get them all. Go ahead and run that. So that's how we crack open the JSON that we get from the model and convert it into a string that we can use inside Python. Now we need to take those strings and convert them into FASTA formatted sequences so that we can visualize them. For this, we can basically copy some of the code that we used above to create these FASTA formatted sequences, like this, for example. We're going to create the AA-0 sequence. We're going to create the ESM2 sequence. And we're going to create the ESM2 3B sequence. And then we're going to write all of those into one big FASTA file so that we can visualize them all together. We'll use this call to seekio.write, but we want to make sure that we also include the wild type sequence and the engineered sequence. Go ahead and run that. Check our files. And there we go. We've got a nice big FASTA file with the wild type, engineered, AA-0, ESM2, ESM3B sequences all there together, easy to work with and visualize. So you know what that means. We have reached the moment of truth for the PETase challenge. There is nothing left to do now except visualize the sequences that we've generated and see which of these 3 AI models, if any, are able to reproduce the changes found by human engineers in 2017. Are you ready? Are you ready? Are you excited? What do you think? You think they're going to do it? We're going to visualize these using exactly the same block of code that we used up here. The moment of truth. Let's see what we got. Aha. Very, very cool. Very, very cool. So how do we do? It looks like AA0 got the W to H substitution. That's replacing a tryptophan with a histidine. ESM2 reverted to a tryptophan, so it just gave us back the wild type sequence with no changes. And same thing for ESM2 3B. Then over here at position 238, none of the models got it perfectly right. None of the models chose phenylalanine. AA0 chose Y, which is tyrosine. The basic ESM2 went with a G, which is glycine. And the expanded ESM2 3B gave us an L, which is leucine. I kind of want to give AA0 partial credit for choosing phenylalanine. If I pull up a table of the amino acids, phenylalanine is very similar to tyrosine with this big hydrophobic side chain. So you could imagine that they would be functionally similar, at least in certain contexts. So I might give AA0 partial credit for that. The results of the PETase mask fill challenge are that none of the models perfectly agreed with the choices of the human engineers. That doesn't mean the models were wrong necessarily. It is possible that these other substitutions could be just as good or better than the ones that the humans found. As far as I know, no one has tested putting a tyrosine or a glycine in that position. I couldn't find that published data. Could be worth trying. I'm biased because AA0 is Ginkgo's model and I wanted it to win, but I'd like to say that AA0 performed a little better than ESM2 on this challenge, even though it's just a small test, not really representative. I think it's interesting to ask why that might be. And I think in this case, the human engineers that chose these amino acids back in 2017, they used a strategy that is not totally different from what an AI model might do. So they looked at a large family of enzymes similar to PETase, and they noticed that a lot of these related enzymes had either a phenylalanine or a histidine in these positions. So in other words, they looked at a pattern in the sequence data and they guessed that the amino acid in nature tend to also give good functionality. And so this is exactly the premise of sequence-based AI models. They also are looking at these same patterns in nature, and when we use them, we are using this sort of inference that the amino acids that nature tend to use are the amino acids that tend to be functional. The AA-0 model is trained with many more protein sequences from our in-house database. Most of those sequences come from microbes isolated from soil samples. So there's a good chance that AA-0 has seen a lot more of these enzymes that are like PETase, but not PETase. So it has a larger sampling depth and it can find deeper patterns. And in this case, it seems like the deeper pattern is that most of these related enzymes use histidine in that position. So maybe we should try using histidine over the tryptophan that specifically PETase uses. And that's the PETase challenge. Congratulations to all our models, and congratulations to you for coding along. You now know how to access Ginkgo's model API and use it for your own protein engineering projects. You can head over to models.ginkgobioworks.ai to sign up for free and get your free inference credits. I am Jake from Ginkgo Bioworks. We are here to make biology easier to engineer. Thanks for watching.